Does everybody have MATLAB on your computers? Yeah, in case you haven't installed MATLAB, in case this is the first time you're using MATLAB, I asked the TA to help you, okay? Like downloading, installing, and stuff like that. So you do need a university account to do that, okay? The MATLAB is now free for all major students. We have the university license. But otherwise, this is how my code looks like. So this piece of code, you can simply run it. And after running, this is what I often do. I will check what variable they are. So here I have a big X variable, which is 2 channels. That's the original recording for all the samples. And in the code, you'll see that I mixed the 2 channels right here. You can see everybody in the back see the screen. Just roughly right here around line 10, there's a mixer. I use 1/3 and 2/3, this proportion to mix 2 channels. Because the audio recording, the audio CD, it has left and right. Let's have a stereo recording, okay? Stereo recording, so I'm mixing everything to 1 channel, and then we perform 6. Now you can just play with this. Number of bits, you can specify the number of bits, and then perform quantization by rounding. Simply rounding to the nearest level, nearest quantization level. Okay, so you can just, in a few lines, you can do that. You can simulate quantization. And then there's the error, right? Error equals to output divided by output subtracted by the input. That's the simulation of the quantitative error. Then you can listen to the error. Okay? So I was listening to it, but somehow it's not so loud. Let's listen to the signal first. Let's check the signal. So you can type sound. From my computer. Not yet. Not there. Strange. Let me get out of MATLAB first. I think I need to launch MATLAB again, so that the audio, the sound card now is connected to this classroom. So just bear with me for a moment. Okay, let me rerun this. That's the quantization error. No, right? So you can seriously wonder, is it white? We were talking about it being white, right? Yeah. So that's why we only have 6 bits. Now how about if we increase the number of bits? Does the spectrum look more flattened? Right, that's the question. So let's increase the number of bits from 6 to 10 and rerun the code. Now we cannot hear the noise, because we introduced 4 more bits. The noise power is suppressed by 24 dB. That's a lot. Okay, so this gives you the. I'm pretty sure when you just listen to the result through your headphone is probably better than just directly through the speaker. Okay, but use a headphone or your earphone, whatever if you have them, and what else? So that's like you can really listen to the quantization error as a random process and question, is it flat or not? Does the sound completely random? Okay? For the 6 bits, it's probably not random. So actually I can use this command, sound scale. And let me just normalize the sound. So this might be pretty loud. Please bear with me. Hopefully it's not too loud. Is it white? Is it white? Does it have a power of delta squared divided by I'm really sorry. This is a disaster now. I apologize. It wakes everybody up. So please make sure you don't listen. No, this is dangerous. Oh, you don't want to use this one. Sound scale if you're on your headphone, could be yeah. Alright, so hopefully please play with this, with some caution, with some caution. Stay away from this command. I was working too hard on this. It sounds pretty white. That, loud noise is pretty white. That's what white noise sounds like. Alright, so that's about homework number 2, quantization error. Okay. Now let's move on. Let's move on to the TA. Can you help erase the board? I can probably do a little better. Let's not use that. But multiply the error by 4 times. That's probably not too bad. But let me check the maximum level. And it's very low. That's why we didn't hear it. Not found SP, but some error. I think I can safely multiply it 10 times and increase the level by 20 dB. Should be fine. White noise, right? This is what white noise should sound like. Okay. All right. So with that, let's move on to our next lecture. Any questions? Any comments? Any comment? Homework number 2. All right. So let's move on to our next topic. Okay. In this next topic, let me open this in another. I think I also have a local copy. PDF is a separate this. Okay, so we have some time to start a new lecture. So the topic will be linear time-invariant systems, and in order to study that, we need a tool called Z-transform. Outline. So here are 2 sections that's in this handout. In the first part of the handout, we will study a few terminologies, quite a few terminologies, so it takes some time. Terminology for linear and time-invariant systems. Okay? A system could be linear, a system could be time-invariant. So that's the kind of terminologies. And the second part is the official introduction to Z-transform. So first things first. Let's talk about linearity, 2 properties. So here we want to define 2 properties regarding a system. So first of all, when we say system, that means in this course, a system. Okay, this is important. System could mean anything, right? Operating system, right? Economic system. But here, when we say system in this textbook, it means something that receives an input and produces an output. Something that has input and produces an output. Okay? That's what a system is about. Where both input and output are time-domain signals. Okay? So signaling system in that regard, system can be denoted by a script H, 早写的 H, which receives an input and produces an output. And usually, the input is called x, the output is called y. It's very simple so far. And the idea is y, the output is a function, is a result of processing the signal using this system. That's simply notation. Okay? Script H. Now then, with this notation, we can introduce two different concepts. Okay? The first concept is called linearity. Linear system. Is a system linear? 线性的系统. So just the first definition is just pretty much the same as elsewhere in any linear algebra context. Linear transformation means that you can first linearly combine two terms, then make the transformation. The result is going to be the same as first making the transformation and then perform linear combination using the same coefficients. Okay? So to read it, h of alpha times x1 plus beta times x2 equals to alpha times h of x1 plus beta times h of x2. That's linearity, simply defined. Okay? So for good linearity, for any given signal, x1, x2, and any given constant alpha and beta is linearity. So if this equation holds for all x1, x2, any given alpha, beta, then we say the linear system is linear only when that happens. That is satisfied. Linearity. Second property is called time invariance. Okay, or adjective time invariant. The system is time invariant. It doesn't vary against time. When time proceeds, when time moves on, the system somehow stays the same. That's the idea. It stays the same as before and will be ever will be. Okay? So mathematically, how do we define it? How do we describe this idea of the system staying the same? Here is a suggestion. Okay? So we say that if we have any given signal, x of n, and when we consider fixed integer n, okay? When we consider fixed integer of n, then x of n minus n means to shift the x signal to the right by n samples. Okay? So then this is the way we describe time invariance of the system. So that literally says that when we delay the input by n samples, the output here also delays by n samples, same delay, nothing else. We delay the input by n samples, the output will also be delayed, the same output, but only at n samples later. Okay? Shift the input to the right by n results in a shift of the output by also by n. If this happens for any given signal, any given input, and if the equality holds for any integer n, for every integer n, positive or negative, okay? Then we can call the system a time invariant system, meaning that the system behavior does not change with time. Okay? Same. You can use the system today, you can come back tomorrow and use the system, the behavior will be the same. Seriously, that's what time invariance means. Or use it 1 second later. Okay? Use it yesterday. Okay? Compared to today, the system has the same behavior. So that's kind of a nice little way of officially rigorously define what it means to be invariant when time proceeds. System stays the same. Two different concepts. So I do want to say that these are two different concepts, which means that the system can be linear but not time invariant. Or the system another system can be time invariant but non-linear. Both can happen. They both can happen. But then when a system is both linear and time invariant, when the system is both linear and time invariant, we call it the LTI system, which stands for linear time invariant. Okay? Now, two different properties. When both are satisfied, we can say the system is linear time invariant or LTI system. So far, so good? Important definitions. Can I move on? Yes? Now, comes an important concept, okay? Just in text, we say any LTI system is characterized by something. It's characterized by what is called impulse response. Okay? So then we need to define impulse response first. When we have a system, what do we mean impulse response? What do we mean the system has an impulse response? And the answer is pretty simple. Impulse response is literally defined as the system's response to delta function, to delta n. As delta n, you know what it is. Delta n having only one, a signal that has only one non-zero center in the middle, right? So that's delta n. So you just use this as an input, put it to a system, and the result is denoted by h of n. Okay? And the result is what we define as impulse response. Okay? Literally the response to a unit impulse. Okay? That is called impulse response. H, taking delta as an input and it produces an output. Okay? That's the impulse response, the definition of any general system. Receiving input, producing an output. Okay? Okay, so keep in mind that any system, not necessarily LTI, any system you can define, you can try to deliver delta function and see at time zero, and then see what's the response, right? So by definition, that's what we refer to as impulse response of that system. So that's good? Okay. But then quickly, if this system is linear and time invariant, okay, two properties, if both properties are satisfied for that system, if the system indeed has the two properties, then important consequence. Okay? This is important. Then the output that we get when we take any arbitrary input, this now is arbitrary, x n is arbitrary. Now when we take any arbitrary input, x of n, the output the system produces is going to be equal to the convolution of x with the impulse response. Okay, and this is an important concept for LTI system. And here we also repeat to write down the definition. What do we mean convolution? The notation that I prefer is to emphasize that we convolve x and h, both are signals, and the result is also a signal as a function of n. So that's just my own notation. But anyway, without any doubt, the definition is in this equation. Okay, convolution involves splitting one of them left, right, and then sum up, making even the sum. Just by default, the summation is from negative infinity to positive infinity, summing of all indices, right? Now, important concept, okay? Only valid for LTI. Okay? Only valid for LTI. For LTI, this is valid, yeah, if and only if the system is LTI. Okay, so in this regard, we say that the LTI system is characterized by h of n. Because if you know h of n, you know pretty much everything about the system. Okay? About the discrete time system. Why? In the sense that you know how to calculate the output. Okay? You know how to calculate the output for any given input. So in this sense, that's how the chip on the side. We can say that the system is completely characterized by its impulse response. Okay? So that's how important it is. You don't need to know anything else. If I tell you there is an LTI system, I draw a block diagram saying that here is an LTI system denoted by script H. The input is xn, the output is yn. Yeah, if I tell you I have a system, you should ask me, then what is impulse response? Because if I tell you the impulse response, then you have stolen my idea. You know everything about the system. You can simulate my system using convolution. You can simulate and say that, okay, now, whenever I receive a signal x of n, I will perform All I need to know is impulse response. I'll just sum up using convolution, and then I can calculate the output. Okay? In that regard, 在这样情况之下 we say the system is characterized by its impulse response. This is all you need to know. Okay? All you need is convolution. No, all you need is impulse response. Okay? But then, at this point, we may ask a question: why? Does it really always hold? Is there any exception? Is there any linear time-invariant system which cannot be characterized by its impulse response? The answer is no. At least the short answer is no. So we need to somehow check it mathematically. This is actually this property. This is a property of LTI system, and it's actually a consequence of linearity and time invariance. Okay? It's actually a consequence, 是一个逻辑的 logical consequence a mathematical consequence 是数学必然的结果the mathematical consequence of the property what L and TI really means. L linearity, TI stands for time invariance. So now next, I invite you to work out this idea. Let's try to show that if the H is LTI, then this equality needs to hold. We need to prove it. Okay, we need to prove that this will hold, it will be valid, and we can show it. Okay, so next, let's begin by this observation. This is a trick. Okay, let's start the proof. The first step of this proof is to realize that we can rewrite any given signal. Okay, we can rewrite any signal as itself on with delta function. So that's one way to say it, but the other way, I like it better. I like the other way to take contemplate on this equality. What do we mean to the signal, any signal is equal to its convolution with delta? What does that mean? So when we have, for example, a signal, positive or negative or could be zero and so on, right? We have a signal that happens in n, okay, and denoted as f of n. So any signal is the collection of all its samples. Let me repeat this. This is almost like, of course, any signal is the collection of all its samples. 每个讯号是由它的 sample 组成的，right? Any signal, any given signal, any arbitrary signal is a collection of all its samples. So that means that, okay, you can regard this signal as it is equal to all the sum of all its individual samples. So that's one signal, right, which is now zero only here. Plus the next sample, which happens right here, only non-zero right there, and elsewhere is all zero. And also before that, that's this sample, right, is bigger and positive. And the summation, you can sum up all of them, all of these samples, and just express the signal as a sum of infinite sum of all these traces. Am I getting clear? But then what is this? If this is time 0, 1, minus 1, 2, 3, 4, and 5. This signal here is x of 0 times delta n. If you notice. Because its height right here is x0, but elsewhere everywhere is 0. Okay? And similarly, what's this signal? How do we write down the expression for this signal? This signal has a height of x1. But now the delta function is shifted to the right by one sample. So this is delta n minus 1. And so on. So similarly, this thing here is x2 times delta n minus 2. So in this regard, we can say that, the signal, any given signal x of n, indeed equal to the summation of everything right here. Equal to the summation, if you take a look, k, summing over all k, x of k, delta of n shifted by k. So that's the idea. That's the way I see this. A signal, any signal, can be expressed as a sum of all samples, shifted at to the right time. Shifted to the correct time. Okay? A signal consists of all samples placed at the correct time. So that's what this really means. Okay? I'm right here. So I'm good now. So that's the way I look at it. But this is almost very intuitive. Hopefully this is intuitive. I think it is intuitive. But then starting here, we can now perform a few tricks. Okay? So now if we just rewrite x of n, any given x of n as this summation. So what do we have? When we rewrite x of n as that, then now we can consider y of n, the output produced by the linear time-invariant system denoted as such. Now let's just substitute x by that new expression, right? Summation k, x k delta shifted to the right by k, and we sum over all k, right? This is just substitution. Okay? Now we need to show that indeed h, what h produces will be y will be equal to x convolved with h. How do we show it? That's the question. Okay? Now is the time we need to start applying the properties of our system. We assume the system is what? Two properties, right? Linearity and time invariance. Okay? Which one will we apply first? Can you suggest? Do we apply linearity first or time invariance first? It looks like let's try applying linearity first, okay? So if h is linear, then we can first perform, this is a linear combination, by the way. This is a linear combination of different delta functions, right? So now we can just pull the summation to the outside. First, perform the transformation and then perform linear combination. That's our idea. That's our idea. Okay, because as much as n is concerned, k is a coefficient. Okay? So now we can do this. This is because of the linearity by assumption. Okay? So that's really nice about this expression. Okay, very useful. So now we are ready to apply the other property, right? What is the other property? Time invariance. The other property is time invariance. Which can be applied to this place right here. Okay. So right here, we shift to delta by k sample. The result should be the output also shifted by k samples, right? As much as the delta function input output is concerned. So the result is shifted by. So this is to apply time invariance. When we have delta function, by definition, the system produces the impulse response. So now we shift the input by k samples. The result should be what? Should be h, also shifted by k samples. That's the way we apply it. So x of k already we are finishing up. Okay? We are indeed finishing up. So this proves that LTI system is characterized by this impulse response in terms of convolution. In terms of convolution. In the convolution sense. So that's why we're running out of time. So this is it. So when we come back next week, we will continue this lecture about different definitions, causality. We have an example. We will introduce the transform. And I have a few remarks. There's a relation between D transform and DTFT, and so it's pretty useful to know that this is all about. Check it out, okay? This is already on the class. Now with that, thank you for being here. See you tomorrow.